welcome to our lecture on the definite integral. In our last lecture, we discussed Riemann sums. Riemann sums are used for estimating the area under a curve. But Riemann sums are limited to continuous non-negative functions, which means you could not have an area underneath the curve. The area needs to be above the curve. So with this formula here, this Riemann sum equation tells you is that the area under your curve is equal to the limit as the number of rectangles gets larger and larger of the sum of the areas of the rectangles. F of x is the height of the rectangle, delta x is the width of the rectangle, and this x star here represents the x value somewhere between the left and the right endpoint, and it could be the left or the right endpoint where you take the height of the rectangle. So this is the value of x where you calculate f of x, and then delta x would be the width of the rectangle. So summing all of these areas of the rectangle together as the number of rectangles approaches infinity gives you the area under the curve. So definite integrals lift the non-negative restriction. So now we'll be having areas above the x-axis and areas below the x-axis. So we say that the definite integral exists when this following limit exists. This side over here is our definite integral. This elongated s is the integral symbol. So the integral symbol, an elongated s, indicates a summation. So the a is called the lower limit of integration, and the b is called the upper limit of integration. Here the word limit is used in a different context. It's not this kind of limit, it's just a boundary, lower boundary, upper boundary. So we call the boundary the lower limit of integration and the upper limit of integration, but not this kind of a limit. All right, so the integral from a to b of f of x dx is the summation of all of the rectangles, infinitely many of them, between a and b. All right, and this is the same as this up here. So now we're saying the area is equal to the definite integral, which is equal to the Riemann sum. So the Riemann sum and the definite integral both yield a number, and that number is the area under the curve. So evaluating a definite integral using the limit definition of a Riemann sum, that would be this definition here, is a tedious amount of work. So we'll use areas and other techniques, mostly geometric techniques, to calculate definite integrals in this section. So when we talk about this example here, we're asked to use the definition of the definite integral to evaluate the integral from 0 to 2 of x squared dx. So we're trying to find the area under the curve between 0 and 2 of the function x squared. All right, so first we figure out what delta x is. So it's between 0 and 2. That's the range of our x values divided by the number of subdivisions n. All right, so then we figure out our function f of x in terms of x sub I. X sub I would be our x within each of those rectangles. So if x sub I is 2I, where I is the index of the rectangle, divided by n, which is the number of rectangles, then we use this x sub I, we place it in the function x squared, and we get this expression here for f of xi. All right, that goes right here in our summation. So that would be f of xi, that's this here, and then we said delta x was 2 over n. All right, so then we can simplify that, and we end up with this summation here, where we took the constant 8 over n cubed outside of the sigma which we know we can do from our properties. So we're basically going to multiply this constant times the sum of I squared. All right, so that's what this statement says, this next line says here. All right, so now we use our rule for summing an integer squared, and we practice with that a little bit. That's this expression here. Subbing that in there and simplifying down to this, we're now ready to take the limit as n approaches infinity of each of these terms, which we can do separately. We can break the limit into 3 pieces using our properties of limits. All right, so now once we evaluate this limit, we can see we've got fixed over infinity. We know that 0 fixed over infinity, 0 here as well. We end up with the constant or the numerical value 8/3, and we say that's our area. All right, so this is the process, briefly, that you would go through if you were going to actually use this technique by strictly sticking to evaluating the Riemann sums to evaluate a definite integral such as this. Now let's talk about signed areas. Areas above the axis are positive areas. Areas below the x-axis are negative areas. The signs occur because the value of f of x is negative below the x-axis, which would cause the Riemann sum to have a negative value. So if we were interested in our net signed area, what we want is to sum all of our areas with their signs attached and get a net signed area. So this would be analogous to finding a displacement. So if you started at a certain point and you went up and then down, then up and then down and up, you're interested in how far you are from the starting point, regardless of how many ups and downs there were. On the other hand, when we talk about total area, what we're interested is the whole trip, up, down, up. We want to add everything up with positive signs attached so we can get an idea of how much blue space basically we have. All right. So next let's talk about properties of integrals. So here we're going to look at the lower and the upper limits of integration. So if they're both the same, that indicates that we have no width to our rectangle, so it would just be a line, a one-dimensional geometric shape. And so our area, of course, would have to be 0 if there was no width. So if you're looking at the integral from a to b of f of x, and then you switch from b to a of f of x, then this switches the sign on the integral. So if you added 2 functions together and then integrated between a and b, found the definite integral between a and b, that would give you the same result of finding the definite integral of the first function and the second function separately between a and b, and then either adding or subtracting those numbers. This property here says that if you take a constant and you multiply it by your function and then find the definite integral, you'll get the same number as if you take the constant outside, evaluate the definite integral first, and multiply that result by the number. You get the same number. Right, and our last property here says that you can break your definite integral into 2 pieces. So let's say we had an interval between a and b, and you had some c between a and b. You can evaluate the integral between a and c and the integral between c and b, add those 2 together, and you'll have the integral between a and b. So next, let's talk about average value of a function. Sometimes we want to find the average value of a function over some closed interval a, b, and we could call that f average. And this would be some average y value that the function had over the closed interval a, b. So if we try to determine what that average value is, we run into an issue. There are infinitely many values of f of x in AB, so we cannot divide by one value to find an average in the typical way. So I don't have a discrete number of points on this graph here. I have infinitely many points. If I had a discrete number of points, I could add those y values up and divide by the number of y values to find the average y value in the typical way. But on a smooth continuous function, you've got infinitely many points, so this method doesn't apply. However, the definite integral gives the exact average value of f of x over the closed interval AB. So in my picture here, I've got f bar representing f average. So we're just going to call it f average, but you may see f bar in other texts. All right, so next, let's look at this line of equations right here. The part that's different is 1 over b minus a. The rest of it, this is your Riemann sum, and this is your definite integral. So this part, this unhighlighted part, is your area under the curve. All right, so this is the new part for calculating your average value of y. So we say that the average value of a continuous function is given, f average, by the definite integral between a and b of f of x dx divided by 1 minus b minus a. So that's this length b minus a. So what this means is that your area under the curve is equal to some average y value times the width of the closed interval. So area equals the height times the width. So we can find this f average by finding the area and dividing by the width of the closed interval. And that's what this statement says here. If you can find the area, and we can using the definite integral, if you divide by the width of the closed interval, that'll give you your average y value. Right, so that's the approach. So we'll do a few examples like this. So this says use a geometric formula to evaluate the integral between 3 and 6 of this square root function dx. Dx just indicates that your function is going to be integrated with respect to x. So your function is a function of x. Next, if we're using a geometric formula, we want to know what type of geometric object this function represents. So we've got the function f of x, which we could say is y, is equal to the square root of 9 minus x minus 3 squared, like that. If you square both sides, you'll get y squared, lifting off the radical. I have this. So if I bring the x squared term over with the y squared term, I'll have this form of the equation here, which we know is a circle from our study of conics. So this has a center opposite sign when you have parentheses of 3 in the x, 0 in the y, and it has a radius equal to the square root of the number on the right-hand side, so we have a radius equal to 3. So if I sketch it quickly on the coordinate plane, I have the top half of a circle. So because I have a plus here, I know that my function, it passes the vertical line test, is only the upper part of this circle. So this is how we would write the upper part of a circle. You write it as a positive square root. If you wanted the lower part of the circle, you would have a negative in front here. So we're integrating between 3 and 6. So I'm going to start here. So I'm interested in finding the area of this quarter circle, basically. All right, so here's where the geometric formulas come in. So we know the area of a circle, of a whole circle, 360 degrees, is pi r squared. But if we have, in our case, we only want a quarter of the area, so that would just be 90 degrees. That would be 1/4 pi r squared. All right, so that means our area is 1/4 pi times 3 squared, which is 3 squared is 9, so our area is 9 pi over 4. So this is equal to the integral between 3 and 6 of the square root of 9 minus x minus 3 squared dx. So we've evaluated our definite integral geometrically. And in order to do this, we converted our function into an equation that we recognize so we could get it onto the graph and figure out what the shape was and how much of that shape we were interested in finding the area of. So example 2 says, use a geometric formula to evaluate the definite integral between 2 and 4 of f of x dx. So we can see that f of x is a line. Y is equal to 2x plus 3. So this is a line. So m would be 2 over 1. And b is 3. So y-intercept of 3, then up 2 over 1. So we're integrating between 2 and 4. So let's get f of 2 would be 2 times 2 is 4. 4 plus 3 is 7. So you've got 2, 7. And f of 4 is equal to 8 plus 3, that would be 11. All right, so I've got my graph. Now let's draw vertical lines to bound our region between 2 and 4. So 2 is here, 4 is here. Now I'm going to shade my region. So that's my region there between the line and the positive x-axis. Okay, so now what I can do to use geometric formulas is break this into a triangle and a rectangle by drawing that line right there, that horizontal line. So now I can see that I've got an easy geometric shape to evaluate. I've got a triangle plus a rectangle. So I know that my triangle would have an area of 1/2 base times height, and my rectangle would have an area of length times width. So looking at my diagram, I've got 11 minus 4, so that's a height of 4 and a width of 2. So my area of my triangle is 1/2 2 times 4. So that would be A1. So we can number our areas A1 and A2. All right, so A2 would be length times width. So the height of that rectangle is 7 and the width is 2. So I've got 2 times 7. So I've got 4 plus 14. That's A1 plus A2. So my total area is 18. So what I've said is my integral between 2 and 4 of 2x plus 3 dx is equal to 18. So this example says, find the net signed area and the total area. So we're going to find both, the net signed area and the total area of this function f of x is equal to x minus 2 over the integral 0 to 6. So the picture is already drawn for us. So we've got a line, slope 1 over 1, y-intercept -2. So that picture is already drawn for us, and we can see that part of the area between 0 and 6 lies underneath the x-axis, and the other part lies above the x-axis. So A1 is going to be positive, and A2 is going to be negative. So for the net signed area, we'd have A net is equal to A1 minus A2. And for the total area, we'll have A total is equal to A1 plus A2, where we're not interested in the signs, but we're interested in the total shaded area. So we have two triangles here, and we know the area of a triangle is 1/2 base times height. So for A1, we have 1/2 4 times 4. So A1 is equal to 16 over 2, which is 8. And we have A2 is equal to 1/2 2, that's your base, times your height, which is also 2. So half of 4, which is 2. In this case, though, we're going to say it's -2 because it's below the x-axis. So now our net signed area, we should say, is 8 minus 2. So our net signed area is 6. Now for the total area, we're just going to ignore the signs basically. So we'll have 8 for A1, 2 for A2. So our total area is 10. So we're just learning the concepts basically now. This may seem a little bit elementary, but we start most of our topics by learning basic concepts, and then we take it from there. So example 4 says, use the properties of definite integrals to write the definite integral of this function, this polynomial, as the sum of 4 definite integrals. So what we're going to be doing is using this property here, which says if you have a function that can be broken up into the sum of several other functions, like polynomial terms can be thought of as little functions, little polynomials all added together. You can break that up into the sum of its parts. So first we'll start out by writing the whole integral. So we've got the integral between 1 and 3, a is 1, b is 3, of the function, the whole function, dx. So now we'll break it up. So that would mean we've got the integral of 1 to 3 of 6x cubed minus integral from 1 to 3 of 4x squared plus the integral between 1 and 3 of 2x minus the integral from 1 to 3 of 3 dx, 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 dx. Now, because we know we can bring out our constant, we can say this is 6 times the integral of 1 to 3 of x cubed dx minus 4 times the integral between 1 and 3 of x squared dx plus 2 times the integral between 1 and 3 of x dx minus 3 times the integral between 1 and 3 of just dx. And that's what we're looking for. So using properties, we rewrote as the sum of 4 definite integrals. Okay, now let's work with properties some more. So we're told that if the integral from 1 to 5 of f of x dx has a value of -3, and the integral between 2 and 5 of f of x dx has a value of 4. Find the value of the integral between 1 and 2 of f of x dx. All right, so we don't need to know what f of x is to figure this out. So we can look at it this way. We've got the integral between 1 and 5 is some number. And let's just shade it. And then we have the integral between 2 and 5 is some number. So if I draw a line here and shade it, I know that the integral between 2 and 5 is some number. So I shaded that blue. Then we're asked, find the value of the integral between 1 and 2. So I can see that I can take the value of between 1 and 5 and subtract off the value between 2 and 5, and I'll be left with the value between 1 and 2. So mathematically, I can write that as the integral between 1 and 2 of f of x dx is equal to the integral between 1 and 5 of f of x dx minus the integral between 2 and 5 of f of x dx. Right, and I have numbers to use in place of those. So the integral between 5 and 1 is -3. The integral between 2 and 5 is 4. So my answer is -7. And this is the integral between 1 and 2 of f of x dx. Example 6 says, find the average value of f of x is equal to 6 minus 2x over the closed interval 0, 3. Also find the x value where the average occurs. So we go back to this definition here for f average. So what we know now is that the integral from a to b of f of x dx is equal to our area. So we need to find the integral between 0 and 3 of 6 minus 2x dx. And that's our area. So if I look at a graph, my function is a line, y is equal to 6 minus 2x. So my b would be 6, and my slope would be -2. So I have this line here. Now, my limits of integration are between 0 and 3. So if I shade that region, I'm talking about this pink triangular region here. All right, so using geometry, of course, we know that the area of a triangle is 1/2 base times height. So my area is 1/2 3 times 6. All right, so that's 18 divided by 2. Our area of the triangle is 9. So now we can say our f average, which we say is 1 over b minus a times the definite integral, which we know is the area under the curve. We can just substitute all of our numbers in and get f average. So f average would be 1 over b minus a. That would just be 3 minus 0 times 9. So that would be 9 divided by 3. So our f average is 3. So that's f average. Now there's a second part of our question. Find the x value where the average occurs. So we know our function is y is equal to 6 minus 2x. So let's say f of x is equal to 6 minus 2x. So we know that f of x is, let's set that equal to f average. So that would be 3 is equal to 6 minus 2x. So I can just solve that for x. So subtracting 6, I get negative 3 is equal to negative 2x. So x is equal to 3 halves. So that's the x value where my f average occurs. So let's see if that makes sense in my picture. So when x is equal to 3 halves, y is equal to 3. 3 halves is 1.5. So we're talking about right there. That would be f average. All right? So that's done. So for linear functions, it's pretty easy to see why that's f average, but the more complicated the functions are, then we know we have these principles that we can apply to more complicated functions. So example 7 says find the average value of this function over the interval 0 to 2 and find the x value where the average occurs. So let's get our definition again. So there's our definition. Now let's look at a graph of our function. So our function says f of x, which we say is y, of course, is equal to the square root of 4 minus x squared, which if I square both sides, y squared is equal to 4 minus x squared. If I bring the x squared over to the left to be with the y squared, I can see I have a circle again, the upper half of a circle, because we have a positive sign in front of the radical. So this would be a center 0, 0, and a radius is equal to the square root of 4, which is 2. All right, so if I look at the graph here, I've got the upper half of a circle centered at the origin with the radius of 2. So my limits of integration are between 0 and 2, so I'm interested in this quarter of the circle in the first quadrant. So let's shade that. Next, we know that the integral from a to b of f of x dx is simply the area, the shaded area, the pink area. All right, so that's the area of a quarter circle. So that would be 1/4 of pi r squared. All right, so r in our case is 2. So this is equal to 1/4 of pi times 2 squared. So that's equal to pi. So next, f average, according to our definition, is 1 over b minus a times that area. So b minus a is 2 minus 0, so let's just put that in there, just so we have it in our notes, times pi. So that's 1/2 of pi, which is pi over 2. So our f average, our average y value in that quarter circle, we're saying is pi over 2. Next, the second part of our question says, find the x value where the average occurs. So we take our function, root 4 minus x squared, we set that equal to f average, and then we solve for x. So root 4 minus x squared is equal to pi over 2. So that means squaring both sides, 4 minus x squared is equal to pi squared over 4. So that means x squared is equal to 4 minus pi squared over 4. So if I take the square root of both sides, I'll have x is equal to the square root of 4 minus pi squared over 4. All right, so that's an exact form of the number. An approximate form would be x is equal to 1.23798. So this is exact. This is approximate. This is exact. And an approximation would be 1.5708. That's approximate. So, as we know, if you're asked for an exact value, that means you leave it in the exact form. So let's go back to our picture. So it's always good to make sense of your answer to see if you're even in the ballpark. In my picture, if x is 1.24, so that would be somewhere here, y should be 1.57. All right, so that means my F average is about right there on the line, of course. I missed it by a little bit, and that makes sense according to my sketch. So example 8 says find the average value of the sine function over the interval 0 to 2 pi, and then the x value where it occurs. So here's our definition of f average once again. So our f of x is the sine function and one period of the sine function, that would be between 0 and 2 pi. So I made a sketch of one period of the sine function. So this would be pi over 2 pi, 3 pi over 2, 2 pi. All right, and then I shaded the bounded region. So you have this positive region, so we can call this A1. And this negative region, we can call it A2. Now, looking at our definition, we can say that F average is equal to 1 over B minus A times our total area in the interval 0 to 2 pi. Okay, now what we can see from this function is that A1 is equal to A2. They just have opposite signs. So A1 is equal to the negative of A2. All right, so if I look at my equation, F average, 1 over B minus A would be 1 over 2 pi minus 0. So A total would be A1 minus A2. All right, and we know that's going to go to 0 because they're equal in size, those two areas, because of the symmetry of the sine function. So F average is going to be equal to 1 over 2 pi times 0, which is equal to 0. All right, so this answers the question, what is F average? Now, what you should be aware of is if let's say your right end point here on your interval was not 2 pi, so your area underneath, let's say, was smaller than your area above, then you could see that F average would not be 0. But since this whole piece is in there and this whole piece is in there, they're going to cancel each other out on this step right here. So F average would be 0. Now let's talk about the x values. So the x values, because of this is periodic function, you can see that there's 1, 2, 3 places where the sign is 0. So that would be 0, pi, and 2 pi. So we're going to list those. Those are the x values where F average occurs. So that answers the question. Okay, so that's all of the examples we have. Let's see, nope, there's one more. Okay, so example 9 says, find the net signed area of the shaded area shown using geometric formulas. So let's go ahead and label our areas. So we'll call this one A1, A2, A3. So our net signed area is going to be the sum of our areas, and we have 3 of them. All right, so that's equal to A1 plus A2 plus A3. All right, and we have to put the signs on them. So we can see that A1 is a half circle, so that would be 1/2 times the area of a circle. So that's 1/2 times pi. You can see that the radius is 1 for that circle, so that's 1 times pi over 2. So that's A1. A2 is going to be the area of a triangle. So we can see, looking at our picture, that that would be 1/2 6 minus 2. That would be 4 for the base and 2 for the height. So 1/2 of 8, that would be 4. And that's under, so we're going to make it a negative area. And then one more area, A3, 1/2 of a circle again. So R in this case is 12 minus 6 is 6. 1/2 of 6 is 3, so R is 3. So that's 9 pi over 2, and that's a positive area. So we have our 3 areas for the 3 regions. Now we need to sum them up. So we have pi over 2 minus 4 plus 9 pi over 2. So that's 10 pi over 2 minus 4. So 10 over 2 is 5. So that's 5 pi minus 4. So this is exact. So this is a net. And then approximate would be decimal form. Plugging that in, 11.708. This would be approximate. Okay, so that answers the question. Evaluate the net signed area using geometric formulas. So once again, this may seem somewhat elementary, but right now we're just trying to digest the concept of definite integrals and that they represent area bounded by the function and the x-axis, and that they can either take on a positive sign above the x-axis or a negative sign below the x-axis. So that takes care of all of our example problems. You should be ready to get started on our homework problems. Let me know if you run into any questions.